Okay, thank you for joining. I will turn this over to Carl Clark, and he will make the introductions. Thank you.
All right, wonderful. Well, good afternoon, one and all. Welcome to the last C2QA Quantum Thursday of this term. We appreciate, we value you all being here to hear an amazing talk that will be had today. Richard Monghe, hopefully I didn't mispronounce it again, is a CUNY City College of New York, true and true. So I'm very delighted and excited and kind of biased as well that he's presenting as a fellow CUNY grad. So first I'm gonna do a bit of introduction about Richard. And I'm gonna go over some of the structure that we hope to facilitate for this conversation. And the key word is conversation. It's not just a presentation. So Richard, as I mentioned earlier, is from New York City. He obtained his bachelor's and master's from the City College of New York in 2014 and 2017 respectively. And thereafter, received his doctorate from the CUNY Graduate Center. Richard graduate studies focus on nanoscale magnetometry using atomic force microscopy. I can't speak today. Richard, please forgive me. With nitrogen vacancy centers in Diamond under the mentorship of Dr. Carlos Morales at City College. Richard is currently investigating surface noise properties of near surface NV centers, nitrogen vacancy centers. So Richard's going to be giving a talk entitled Suppression of Noise of a Single Spin Diamond Probe in Proximity to a High Temperature Superconductor. Again, this is going to be an amazing conversation that we're going to be had. Please reminded for those who've joined us previously that there will be certain transitions in the conversation. During those transition points, the floor is going to be open up for questions. So we're going to be stopping the presentations. We're going to ask you if you have any questions. You can always place your questions in the chat, raise your hand, and we're going to make this a conversation as best as possible. Again, this is the last Quantum Thursday, and we appreciate you all being here. And without further delay, Richard, the floor is yours.
Yeah, thank you, Carl, for the introduction. So yes, my name is Richard Mohe. I am CUNY, City University of New York, true and true. I have attended City College. I am currently working at the City College campus with Professor Carlos Morales. And specifically, my specialty is doing scanning probe microscopy with quantum isolated systems in solid state, not in solid state systems, and specifically in diamond. So that's what I would talk about. I would talk also about the sort of phenomena that we observe, the dynamics of surface properties of this diamond in proximity to a high temperature superconductor. So just as a brief introduction into my into the outline. First, I will give a personal background, then I would do a bit of introduction and the history in weak magnetic field detection. There were some early proposals back in the late 90s to early 2000s. And then I will get more into the nitrogen vacancy center, which is the defect that we use to perform this magnetic field sensing. Then also some overview on some of the surface noise that sort of plagues near surface NVs and their spin properties. And then I will get into my work, into my contribution into that field, into the understanding of these surface noise properties. So my background, just to go over this briefly, my parents are from Guayaquil, Ecuador. Is a city near the sea. Well, it's near the ocean. The gastronomy is very nice. It's mostly seafood, although I cannot eat it because I'm allergic, which is it's a bummer. But And Ecuador is right there, and South America is called Ecuador because it's in the equator. And also, sadly, we just got eliminated like 2 days ago from the World Cup. It's okay. So, yeah, so it's here. So my parents immigrated from Guayaquil, Ecuador to New York City for a much better life. Like Carl mentioned before, I was born and raised in New York City. What you see on the screen are all the schools I've ever attended throughout my entire life. And I haven't pretty much moved within like a 2-3 mile radius for my entire career. Lastly, I after going to high school in the Harlem School, I attended the City College of New York. I did my bachelor's in 2014 and 2017. But my career as a bachelor's and a master's was a little bit different from what I am doing now, because during my career in physics, I did not do any research at all. My concentration in the physics field was in secondary education. I attended the School of Education. I got my certification to teach. And after I graduated with my bachelor's in 2014, then I worked as a tutor for this nonprofit organization, this after-school program called the Harlem Children's Zone. And I was tutoring and giving after-school classes to Harlem students from Harlem charter schools and Harlem public schools. Then, while working for the nonprofit, I was working on obtaining my master's from the City College of New York. And there I realized, okay, I have no research experience. I need to do some research, because I wanted to see how it is, because I never had that exposure during my bachelor's. Then I joined, during my master's, I joined Carlos Medeiros' group in 2016. And then shortly after, I applied for the doctoral physics program in 2018. And now currently I am a 5th year PhD student. So I know the C2QA is geared towards an audience of undergrad and graduate students. And I'm probably, I don't know, you guys can correct me, probably one of the few grad students that actually is presenting the C2QA Quantum Thursdays. So it's a pleasure to be here. So now we'll get more into the science part. I'm sure there's not going to be any questions about my background, but I will continue more now into the science. So detecting weak magnetic fields at the nanoscale has been a really interesting topic due to its potential to its potential applications in biology. If you want to monitor mechanisms in cell membranes and technology, one can use these magnetic field sensing to sort of probe currents in small electrical circuits. And detecting weak magnetic fields and doing this sort of imaging can bring forth new wealth of knowledge of fundamental physics happening in condensed matter. So the first proposal in 1996 by Sikatsky and Letokov mentioned the use of single molecules to perform nanoscale optical imaging and sensing. And then they mentioned there that the excitation energy from the probe molecule can be transferred to fluorescent centers on the surface of the sample. And here they don't specify what sort of sensing it is. And then later, some sort of sensing, I don't think they do specify magnetic field sensing, to my knowledge. But in 2005, Chernobrod and Berman, they proposed using individual spins to probe very weak magnetic fields. And the basic principle relies in here, this proposal, on microwave-induced spin transitions, or radio frequency induced spin transitions, which can ultimately be detected via the change in the luminescence intensity of that spin. So then how do we then obtain these individual isolated quantum systems? And the best candidate is our solid state system, because they have the ability to host many defects, and there's also wideband semiconductors, in particular diamond, are very good candidates. So that's what I work with diamond. And as most of you know, diamond is a wide band gap superconductor, and diamond is made out of the carbon element. During the formation of diamond, you have these substitutional atoms or other complexes that emerge during the formation. You have these defects. So these defects give rise to special localized electronic states that allow for the absorption and emission of light at specific wavelengths, which it gives diamond the beautiful color. Hence also the name for these defects are color centers. Depending on the sort of defect, you get some particular color, either be it vacancies, nitrogens, silicon atoms, boron, etc. So in particular, I want to bring forth to your attention this graph here. So importantly, these defects lie deep within the band gap. So it behaves like an isolated quantum system. And essentially rendering them as isolated atoms which makes those defects amenable to precise manipulation. The defect and color center that we use is the nitrogen vacancy center in diamond. So this defect is composed of a substitutional nitrogen atom adjacent to a vacancy. This defect is efficiently excited by a 532 nanometer laser, and its photoluminescence is in the range of 637 to 800 nanometers, 750 nanometers or so in the near red infrared range. And these defects have been individually isolated in 1997 for the first time via confocal microscopy. So you can address them individually. So the following that you see on the screen is the energy level scheme of the nitrogen vacancy center. And the essential feature of the NV center is that their ground state is a spin triplet with the spin 1. And this arises due to the fact that there are two unpaired electrons in the negatively nitrogen vacancy center. So that's something important I need to point out. There's two charge states, is the negative and the neutral. And there's also a third one, a positive. But just when I mention nitrogen vacancy center, be sure to put it in your mind that what I'm talking about is the negative nitrogen vacancy center. So the two spins that I just mentioned previously, they have a spin-spin interaction that induces a splitting of 2.87 gigahertz here in the ground state between the ms equals 0 and ms plus 1 states. So the key property of the NV center is the ability to initialize and read out this spin state optically. So the photoluminescence is higher in the ms equals 0 state. So the fluorescence is higher when the ms equals 0 state is heavily populated, that's the spin state. So this is possible because of the spin-dependent non-radiative decay through the metastable singlet states. And spin initialization is also possible under continuous excitation with the green. So with these two properties, the initialization and optical readout abilities, we can optically detect the electron spin resonance. And this is what we call optically detected magnetic resonance, or ODMR for short. So as you can see, if we apply a microwave field resonant with this zero field splitting at 2.87 gigahertz, we observe dips in the fluorescence And we can take this a step further and apply a magnetic field, observe the Zeeman splitting. And from here, we can quantitatively obtain the magnitude of the magnetic field. So you can see the splitting there. Also, another powerful tool is that from the position of these peaks, one can also calculate the orientation of that field with respect to the NV axis, which is another powerful tool, because not only you can think of doing a magnetometry, just DC magnetometry, you can now perform like vector magnetometry now as a function of position, determine the direction of the field using the sensor. So the NV center is one of the advantages of the NV center is the ability to apply pulse protocols. We can now apply pulse protocols to perform much more integrated spin manipulation techniques. So just as a brief example, we can write the duration of the microwave field to see these Rabi oscillations. And from here, we can define a pi pulse, a pi over 2 pulse, and those terms rings a bell in the nuclear magnetic resonance community, because now you can now do some spin manipulation sequences to the NV center. In addition, we can monitor its longitudinal and transverse spin relaxation times. And this is known as the T1 and the T2. Those, when I think of the T1 and T2, I think of MRI imaging. So the T1, the longitudinal spin relaxation time of the NV center, and the T2, the transverse spin relaxation time, can be obtained. And these are some of the following examples. The NV center exhibits T1 lifetimes around the millisecond range. And the T2, the transverse spin relaxation, is around in the tens of 100 microseconds range, or even single-digit microsecond range, depending on the proximity of the NV center close to the diamond surface. So these relatively long relaxation times make it a good candidate for quantum information processing. Now, specifically, these are metrics in which are used to determine if a quantum system is best suited for quantum information processing. So because specifically the T2, how long would the spin state remain in the superposition will determine how many operations you can do within a specific time. So much work in the past decade has been focused on integrating the NV center into scanning probe microscopy. So to my knowledge, and I think this is the case, the first known NV-based scanning probe microscopy of magnetic fields was done by Bala Subramanian paper in 2008, this Nature paper, where they picked up a nanodiamond containing a single nitrogen vacancy splinter. And here they were able to observe dips in the fluorescence when the electron spin frequency is in resonance with the microwave driving field frequency. And you can see here, there are dips in the fluorescence, again, because of this optically detected magnetic resonance effect. Then next, shortly after in 2012 is where things really took off, because now an all diamond probe was nanofabricated and integrated into an atomic force microscope probe. And this is in here in this paper, they perform magnetic field imaging scanning containing single NV centers, and they were able to achieve that through implantation and I'm pretty sure many iterations of many of these cantilevers hosting these nanopillars, but there is a single nitrogen vacancy center at the apex of that. And yeah, they were able to image these magnetic fields with really high resolution of these magnetic domains in a hard drive. As you can see, the resolution is nanometer resolution. So after this, so after this, in all diamond probes have been used since then, and all that I mentioned before were forms of magnetic field sensing. So for example, in this paper, they were able to monitor the shifts of the ODMR to map out the antiferromagnetic order in this material. So another paper, another example of NB-based scanning probe microscopy is this paper by Ariyaratne Anyayayic group in 2018, where they perform a T1-based map using these NV centers. They scan the NV center and perform T1 relaxation measurements on that NV center, and then from the T1 obtain the conductivity of that nearby metal film. So you can see they also mapped out these nano patterned metal films in here. So that's really nice application. Another one is electric field sensing. And in here in this paper, they use a specific pulse protocol to enhance the sensitivity of the NV center with electric fields. And they attribute like a strong electric field screening effect at low frequencies, depending on this pulse, this, like I mentioned, this pulse protocol, due to charge noise at the surface, which is what I'm going to be talking about. There are many things happening at the surface of the magnet. And there are other forms of sensing not yet shown with scanning probe microscopy, to my knowledge, like strain or temperature sensing. But those strain and temperature sensing has been done in bulk diamond, of course. So the NV sensor is sensitive to all of these. Okay, I'm going to take a break. Just from my presentation. But if you have any questions, I'm here to answer them if there are any questions so far.
All right. Are there any questions? Again, you can use the hand feature, unmute, or place your questions in the chat.
Hi, yes, you talked about this. You may have touched on this earlier with your background, actually. So what sort of led you from wanting to do teaching with the program that you were with to gaining your doctorate?
Yeah, that's a very good question. I guess my interest in physics was always there as the bachelor's. My love for physics was very great that I wanted to teach people, and I that's why I went into teaching. And people have told me that I have really good teaching skills, so that's what led me to go into there. So I guess the change in the career came from the fact that, I still didn't completely change careers while doing my master's, because I was doing the teaching at Harlan Children's for the nonprofit. But I wanted to know what it was to be in a laboratory, because that's what I felt was missing from my experience in my undergrad. And teaching is not something that I'm still putting aside, even as doing my doctorate at the moment. I still do teach, but now is at a college level, and I still do visits at high schools, like because I have previous colleagues there. So it's not something I've put to the side of yet. I believe my career in physics has always been towards gaining more knowledge into the field. That's why, I guess I went into research. But
All
yeah, it's hopefully I answered your question.
Yeah, thank you.
So I see a future professor, amazing professor as well, in front of us. All right, we do have a question that is in the chat. The
Sure.
question goes, is there an estimation on the role of THZ higher frequency bands to the noise contribution?
Oh, okay. So I know, so the higher frequency bands, yes, I will get into that. There is some slides that I do have, but yes, there is a role that higher frequencies bands play to the noise contribution. And at some point, the higher frequencies that are probed, so I will get into this soon, but there is some protocols that one can implement to sort of filter out noise at these specific frequencies. And I know that in the terahertz range, the noise spectrum seems to, I think, plateau. So to my knowledge, that's what I know about the terahertz range contribution of the noise. But yes, there is some higher frequency sources into the decoherence of the spin. Yes.
All right, so that means more to come. All right, there's no additional questions, so proceed and we'll see where this goes with that piece you're just talking about.
Okay, yeah, sure. So, okay, let me click. Okay. So in order to increase the sensitivity of the NV center, we need to place the NV as close to the surface as possible. And this makes sense. I mean, the analogy for me is like if you have a metal detector on the beach and you want to find treasure, you need to put that metal detector as close to the sand as possible. This is pretty much this is what it is. But there's a trade-off. There's a huge caveat, and this is to maximize detected signal, you need to put the sensor close to the surface. However, as probably most of you know here already, there's a trade-off. And then many experiments show that that the spin lifetimes of shallow defects are much shorter than the bulk counterparts. Another thing I did forget to mention is that another reason we want to place the NV center close to the surface is also for higher spatial resolution as well. So, okay, so like I mentioned, there are many experiments showing that the spin lifetime shallow NV centers, as it gets shallower and shallower close to the surface, the spin lifetimes are much shorter than the bulk counterparts. As you can see here in this New-Feng Wang paper in 2016, they etch the diamond and they look at one specific NV, they etch the diamond and look at the T2 as a function of depth, distance from the surface. As you can see, it decreases already in the tens of nanometer range. There's already a decrease in the coherence. So there is enhanced magnetic noise and reduced spin lifetimes of the surfaces or interfaces of the diamond. And this is a well-known phenomenon that has been studied in the context of superconducting quantum interference devices and donor spins in silicon. So this enhanced source of noise is mostly from the surface of the diamond is mostly attributed to magnetic noise from unpaired electrons or electric field noise from surface charges. And they dangling bonds terminating surface atoms, maybe such as oxygen or hydrogen, or absorb molecules or maybe strain at the surface are possible origins in dynamic strain, are possible origins of the noise that have been suggested in the past. Therefore, learning more about these surface dynamics can provide some insight on ways to mitigate that surface noise. and ultimately giving us, ultimately with the goal of improving the sensitivity of the NV center. Because another thing that is also is a metric for sensitivity of the NV center is also the T2 lifetime. So we want to get rid of this noise to increase the spin lifetime. Like I mentioned before, the recent work in the past decade has focused on integrating the NV center into scanning probe microscopy through the use of these special AFM probes. And these probes have been fabricated to host a single NV center at the apex. And this is nice because these AFM probe makes it possible to bring that NV center as close to the sample as possible. So using the ODMR, in here, for example, they were able to map out the magnetic field from the vortex on top of a superconductor when the superconductor is in the mixed state. So one of the advantages, like I mentioned before, of the NV center is the ability to implement time-resolved protocols via a series of microwave pulses, like the Rabi oscillations that I showed you. So we can implement like a pulse like this. One can engineer a pulse to filter out specific frequencies and obtain information about the source of noise that's responsible for the NV spin lifetime or decoherence. So similar to known techniques in magnetic resonance imaging, like I mentioned before, this form of transverse spin relaxometry based on the Hahn echo, because this is a Hahn echo sequence or related multi-pulse trains, like I will get into CPMG, they convey valuable information because particularly the timing structure of these pulse protocols can be adapted to expose dynamical processes that are not apparent via the DC sensing, because the DC sensing, all that I mentioned before was DC sensing, where if you want to map out the magnetic field, it's a static magnetic field. The magnetic field is not changing with time. But with AC sensing, you can expose things that are not apparent through this standard form of sensing. So work in the past, specifically, for example, in Jacobi's group, has focused on investigating the issue of surface-induced decoherence of NV spins. So notice as they bring the probe closer to the nearby element, they observe a decrease in decoherence lifetime. And by implementing this protocol, they are imaging the fluctuating magnetic fields from that nearby diamond surface. Then the spectral properties from the surface electron spins can be extracted from these decoherence curves. And by using the mentioned techniques, we investigate the source of noise responsible for the probe's decoherence using a nearby high temperature superconductor. So this is where I get into sort of now into my work. So this is our setup. We have the diamond probe that I've been mentioning all along with the single nitrogen vacancy center at the apex and nearby RF wire to drive the NV center. And here we have a superconducting patch, a thallium barium calcium copper oxide high temperature superconductor, TBCCO. We have a corner patch here. And one thing I want to remind all of you is that when a superconductor is in the superconducting state, it does two things. It exhibits zero resistance in electrical transport, and it will exclude any applied magnetic field. And this has a name, it's the Meissner effect. And if we use the NV sensor to scan over this corner of superconducting material, we observe an expected DC Meissner effect, where the magnetic field magnitude is less on top of the superconductor. It's somehow shielding it. So it's, as expected, it excludes that applied magnetic field. So we see this lower magnetic field magnitude. Another thing we do observe is a high frequency response from the superconductor. So, and this is apparent from the ODMR contrast. So the ODMR contrast is indicative of the microwave driving field strength. And as you can see, is changing as a function of position. So the superconductor is inducing currents in this AC regime at this 3 gigahertz regime in response to the micro driving field coming from the RF wire. So that Audemars contrast is changing as a function of position. So then with this in mind, we can implement the protocols that I mentioned before, like an Hahn echo sequence. So we have a diamond nanopillar, this NV, single NV, in close proximity to the TBCCL, to the high temperature superconductor. As you can see, this is the coherence curves. So just to explain the curves a little bit, these collapse and revivals are due to nearby coupled carbon-13 spins. And the frequency of these collapses and revivals are due to the carbon-13 Larmor frequency in the applied magnetic field. But I just want to bring to your attention just the envelope of the curve, because the envelope of the curve is what gives us the T2 lifetime. When we take the probe off the superconductor on the substrate, we see a T2 of 28 microseconds. And this is a T2, the native T2 of that NV center. Then when we take the NV center and put it on top of the superconductor, we observe an increase in the T2, 43 microseconds of T2, an enhancement due to this superconductor. To confirm this effect a bit further, we now are going to change the Z. We're going to remain now on position A on top of the superconductor and change the distance. And we still observe the same effect that at 150 nanometers away from the superconductor, we get 43 microseconds, and 3 microns away from the superconductor, the T2 spin lifetime is 29 microseconds. So the superconductor is doing something. So taking this a step further, plotting this as a function of position, we clearly see a trend in here. And so the superconductor is somehow mitigating that surface noise from that MV center. So in addition to this, we wanted to get rid of any sort of anomalies in terms of frequencies. And we implemented this following dynamical decoupling sequence, the Carr-Purcell Maybloom Gill, CPMG, I'm just gonna call it CPMG, sequence, to observe that, to see this sort of effect at different frequencies. I don't think we got to the terahertz frequency with this. This is because I think for terahertz frequency with CPMG, we need to put I don't know how many pi pulses. I will have to do the calculation, some back of the envelope calculation with terahertz. It would have to be a lot of pi pulses here. But as the number of pi pulses increases, so does the coherence lifetime of the NV center. So these are used to filter out specific frequencies. So with this sequence with CPMG 8 being the number of pi pulses that we have in this sequence, we still observe the same effect. By the way, this is a different probe. That's hence the different number of coherence, but still relatively there is a change, the T2. And no matter how many pi pulses we use, there's 200 nanometers away from the superconductor, we have that T2 increase, as opposed to away from the superconductor. So the superconductor is definitely doing something. So there's clearly a chain that shows the effect the superconductor has on the source of noise, which can come from either magnetic field noise from paramagnetic centers or electric field noise from surface charges. So we will get into that soon. I think I could probably take a break now and then probably I think answers briefly some questions and then move on if there are any.
I think that's a good idea. Okay, so again, please raise your hand, unmute, or the chat. Teachers always wait 4 seconds. Okay, no questions, so we'll continue. And then again, the floor is definitely open for any questions. So please share them as they arrive.
Yeah. Okay. So we'll continue. So now we take this a step further. We implement something that I think, I mean, it probably has been done before, but this is a pretty interesting technique that we've developed where, like I mentioned before, both the magnitude of the magnetic field is changing as a function of position, and the microwave driving field strength is also changing as a function of position. So as you can see from the audio mark contrast and the field shift from these two maps that I showed before, you can see more the NV frequency on this line cut and the pi, the Rabi frequency. So in order for us to implement the Han-echo sequence put here with the pi over 2, pi and pi over 2 pulses, we need to do two things. We need to, as a function of position, change the microwave frequency to resonantly excite the NV center. But another thing we need to do is also apply a correction in the microwave driving field strength as a function of position to keep the pi pulse duration constant in all these sequences. So this is precisely what we did. So in here, I performed a Rabi frequency line cut across this interface of superconductor. As you can see, at some points in here are some examples of the Rabi frequencies. And there's a lot of variation, but after applying my correction, there is now a constant pi pulse. Now there is a defined pi pulse, which all of them share, all of these positions share. So now, then we can implement the T2 sequence. And as you can see, we confirm our effect. On top of the superconductor, there is higher T2, and outside the superconductor, there's a lower T2. There's also something happening in the interface, which we have not yet simulated, but we rationalize that to be the shape of the probe that we use, which comes into the interpretation next. So now yes. So now what we do is now have to consider the sources of noises of the NV centers, either coming from paramagnetic centers at the surface or from surface charge fluctuations, giving rise to electric field noise. So what we do is that we consider mirror charges at the superconductor. And if we do, we can see an enhanced magnetic field magnitude on top of the surface of the of the diamond, and due to the mirror charges of the superconductor. So we rationalize this as a redistribution of local charge. This is what's happening. And the presence of these image charges lowers the intercarrier repulsion energy. And the higher the surface carrier density, which comes from the fact that there's now low intercarrier repulsion energy, leads to a growth in the spin coherence lifetime. Using an ohmic model, we sort of simulate that, and we come up with this equation. And from this equation, depending on the frequency that we probe, we see that a lower resistivity or higher conductivity leads to a lower spectral noise or higher coherence times, which is in qualitative agreement with our observations. So, and we take this a step further. We can see that there is a qualitative agreement. We get like around the same range of coherence enhancement doing this modeling, around 40% of enhancement, which is what we observe. We observe also at the order of 2, almost at the order of 2 enhancement, but it's in qualitative agreement. So just, I guess to kind of summarize, I guess this is also, we're coming close to the conclusion. So to summarize, we observed the Meissner effect, which was expected. But however, what was not expected was the T2 enhancement. And like I mentioned, where is the source of noise coming from? How is this noise being suppressed? There are 2 sources. There are magnetic field fluctuations. By the way, I don't know, it's interesting, I mean, there hasn't been any question, but I didn't pay attention to the magnetic field fluctuations. So why is it? So the reason for this is because our simulations, considering also surface currents and also mirror dipole moments, which I haven't included here, unfortunately, but considering both of them, our simulations, our calculations do not agree with what we observe if we only consider magnetic field being the main source of noise. So there's not enough magnetic field shielding coming from the Meissner effect from the superconductor, because we are even at the micron range, we still get some enhancement. So all of these results suggest that the main source of the coherence is the electric fields, and electric fields, according to our calculation, can be shielded to that extent at that range. And this is all work that have been submitted, is in archive. It's currently under review. There's also work in the past that has someone contributed to this insight, where in Daniel Rugar's group from IBM in 2015, they observed that they concluded that the main source of noise for near surface NV centers is electric fields, and they used this oil to sort of increase the dielectric constant near the surface, and they observed an increase in the T2, and they concluded the main source of noise is being the electric field. So this brings prospects to increase the bandwidth and sensitivity of the NV center, because now we can think of ways to sort of terminate the surface of the diamond. Maybe we can deposit, I don't know, maybe like a thin film of metal on the surface of the diamond and increase the T2. But this gives us some insight of how all of these dynamics work. And our future work will most likely use these coherence curves and extract spectral densities from them. So we can take the T2 close and away from the superconductor, take the spectral density, subtract them, and obtain information about the sample itself. And perhaps we can get information about the frequency pinning of the vortices, which arise due to the superconductor being in the mixed state. So yeah, I guess in here I will sort of end it. So just to give thanks to every person that was involved in the project, because it was a long time coming. It's putting this scanning microscope together has been pretty much like most of my journey as a grad student, trying to make this work. And we use Kinami probes, and yeah, just give thanks to everybody involved in the funding. If there are any questions, please can go ahead and ask.
All right, once again, thank you, Richard. The floor is open for questions. So let's have a conversation.
I have a question, Richard.
Yes.
Are you collaborating with anyone at Brookhaven in this effort or in other efforts?
Brookhaven for this, not specifically, although I know there is some research along the lines of trying to investigate the surface noise. Well, that's not really technically collaboration, I guess, but yeah, I mean, there's been discussions with people at other groups, I guess, to give us insight into this phenomena. Yeah.
Yeah, I know there's some other work happening in this area with some of our other partners within C2QA, but I see some other hands up. If I may just throw out a question now, and then you can answer this question after you've responded to the others. My question really is, what advice would you give to students who are either in these areas that are directly impacting quantum information science, or those who are adjacent and majors that may provide some value in any kind of workforce opportunity within QIS? What advice would you give to the students in those areas?
Yeah, so yeah, this is a pretty good question. I think that any sort of experience is always in the field of research is always enlightening, because not only you learn skills particular to the niche field that ultimately one is going to end up studying, but you learn skills that are transferable to any other forms of any other sectors of work. So, for example, so I guess the second question is also like, if somebody's adjacent to this field, what can drive them to go into the quantum information sciences? And yeah, I guess it kind of ties in with my first question, where well, I was adjacent to the field, I guess, because I was in education, and I ended up being in research. So one thing is that I gained so much knowledge, not only because if you want to study quantum information sciences, yeah, go for it. I would say 100%, just go out there and do some research. This is actually how I got to ended up doing research with Carlos Meriles, because when I was doing my master's, I sent out emails to a lot of professors, and he was the only one that got back to me. And then I ended up, working with him. So one for sure is just, take advantage of any opportunity that's out there, because even if it doesn't end up being what it is for you, then you'll know what is for you and what is not for you. And secondly, you learn skills that are not only particular to the field that you're doing research on, they're, like I mentioned, transferable. Mm-hmm. And yeah, I guess hopefully that answered the question.
That definitely answered the question. Thank you. I didn't want to cut off anyone else. I know Peter had a question.
Right. Before we get to Peter, I do want to also add to Richard's response. You meet great mentors such as Carlos as well along the way. So you may not go directly, or you do, but at the same time, you do meet individuals that would advocate for you. All right, Peter Shushko, are you still there with your question?
Yes, I am. Thanks.
All right,
so it's about the origin of electric fields, the microscopic origin of electric fields. So you identify them as a source of noise, right?
Yes.
And so can we narrow? Is it possible to narrow down what these electric fields are due to? Are we talking about individual defects, for example, at the surface? Maybe some surface structure, topological features such as steps or some corners. Maybe it's a source of this noise is track that is formed during the implantation. Any kind of ideas about that?
Yeah, so there is a lot of work on investigating that source of noise. I know that there's many groups before us, like Natalie de Leon's group or Yayi's group, where they have investigated that source of noise by implementing a double electron decoupling sequence, I believe, the deer sequence, and there you can actually now get the signals from what is exactly the source of noise. And there they do attribute that to electrons, which they can see in the deer frequency, and the applied magnetic field kind of coincides with the gyromagnetic, with the frequency expected for the electron. So there's been work in that regard. There's also been work on playing around with the surface termination of diamond as well, and seeing the effect this has on the coherence time. And in addition to that, not only in Rugar's paper that I mentioned briefly, there's also been other papers where they do deposit something else other than oils. Like I saw a paper recently of putting PMMA on the surface of the diamond, and also seeing the coherence lifetime increase. But the specific sources, yeah, they're due to just electrons because of dangling bonds because of imperfections of the surface. And that has been probed with some of these post protocols and pinpointed it to be these electrons. And in addition, yeah, there was a paper recently, I know Raktrup is the last one in the group, where they use a electric field to change the surface dynamics of that diamond surface. And they can also observe the same effect, where if they alter the arrangement of charges at the surface, they can enhance the T2. And that's because they are driving away these electron charges away from the surface. So hopefully I answered your question, but yeah, so that's my answer.
Okay, we're short of time, but we do have one quick question. What were some of the temperatures of the scans?
That's a very good question. Yeah, that's a very, very good question, because that's was one of the questions from one of the reviewers, which was, is this effect temperature dependent? I don't have it here. Let's see. Hold on. This is going to be an impromptu. Let's see, an impromptu PowerPoint. I guess session. So I'll show you here. So yeah, some of the ranges that the temperature scans were done, we did them at various temperature ranges. And we can see the Meissner effect sort of disappearing as a function of temperature. So let's see, do you still see my screen?
Yes, we can.
Yes, you do. I am gonna create a slide, and oh, there you go. So these are the temperature ranges that we have done. So we did it from 90 Kelvin up to above the transition temperature of the superconductor. You can see that the Meissner effect disappears. And these are the temperature ranges in which we did the scans. And you can also see that the effect of the coherence enhancement disappears above the transition temperature of the superconductor. Therefore, making it very making it required that the superconductor needs to be in the superconducting state to observe this effect, because otherwise we will not see this effect. There might be some other sources of noise, like Johnson noise, that do arise from higher temperatures that it's well known to happen in metals. But yeah, these are the temperatures we did some of the scans.
All right, thank you, Kim, for asking that question, because without that, we would not have gotten an opportunity to see this so clearly. So thank you so much. We are bound for time. So Richard, thank you so much for the presentation. And again, we appreciate you closing us out for this Quantum Thursday series. Again, its design, or one of the designs, is to encourage and engage students to go into quantum science, and they also be part of the science learn about the part of the science that's already taking place within C2QA, as well as the C2QA network. So for everyone that joined us this term, please note we're coming back in the spring, so there'll be more wonderful presentations and conversations. But for now, Richard, thank you so much for this talk. And to our students that are in the audience, you are in the right place. So whether you are directly or adjacent, this is the right place to learn, but also the right place to be right now. Everyone, please have a wonderful, wonderful afternoon, and we hope to see you in the spring. Take care, everyone.
Thank you, Carl. Thank you, Richard.
Thank you.